It gives me great pleasure to introduce Yudong Chen. So this may be a slightly long introduction because Yudong and I go back quite a long way. We were actually office mates together, and if I remember right, I was actually his TA for probability. So I have a lot of stories about Yudong, so the talk will only be for half an hour, the rest of it is me. No, but okay, in seriousness, so Yudong is he just joined last year in the Operations Research and Information Engineering School. And before this, he did his PhD at UT Austin in the ECE department with Konstantin Karmanis. And then after that, he did a postdoc at Berkeley with Wainwright, and then he's come here. And along the way, Yudong has done some very fundamental work in thinking about matrix completion, in community detection and clustering, and more recently on non-convex optimization. And today he's going to tell us some things about statistical and computational trade-offs in community detection. So over to you.
Yeah. Thanks a lot for coming and for the introduction. So a large part of my research has been focusing on understanding the interplay between so-called statistics and computation and their trade-offs. And in this talk, I'll talk about that, and I'll focus on a specific problem, which is community detection, or so-called graph clustering. And this is joint work with Jiamin Xu. He was a PhD student at UIUC, now a postdoc at UPenn. So in statistics and machine learning, we all know that our goal is to work with data and to extract information and structures for your data, from your data. And when we design machine learning or statistical algorithms, there are several different issues that we want to consider. For example, there is a computational issue. We want our algorithms to be fast, to have lower running time, to be able to handle larger data sets, and we want our algorithm to be easy to implement. So this is the computational aspect when we think about designing a machine learning or statistical algorithm. And we also have a statistical aspect of the problem. We want our algorithm to be robust, to be able to handle data that is very noisy, and to give you an accurate estimate even when you have a lot of noise in your data. And we want our algorithm to be able to learn very complicated structures from your data. So we have these two different types of issues that we want to think about when we design a machine learning or a statistical algorithm. And here is a very simple toy example. So suppose I give you n samples from a Gaussian distribution with unknown mean, and our goal is to estimate the mean of this Gaussian distribution from these n samples. And we all know that a simple algorithm is just to take the average of these n samples. And what's the statistical and computational properties of these algorithms? So computationally, this is a linear time algorithm. It takes time, O(n), to read all this data. So we need that much time to compute this estimator. And statistically, we can compute its expected square error, which is 1/n, because we are averaging n independent variables with unique variance. So this is one possible algorithm for estimating the mean of a Gaussian distribution, but can you think of another algorithm that is even faster? This is a linear time algorithm. Can you do better than this computationally?
To take our first example.
Yeah. So there's another trivial algorithms that you probably don't want to use in practice, but you can just take the first sample as your estimate. Computationally, this is a super fast algorithm. It takes constant time. But statistically, its expected square error is a constant. It does not go down when the sample size increases. So we have these two algorithms for the same problem. Computationally, the second algorithm is better, but statistically, this is a much worse algorithm. So you see there is this trade-off between the computational aspects of an algorithm and the statistical aspects of the algorithm. And in this talk, I want to understand this trade-off for more interesting problems than just estimating the mean of a Gaussian. And I want to do this in a more qualitative way to quantify this trade-off between statistics and computation. And again, if we look at the spectrums of all learning and statistical algorithms, in the one end, we have algorithms that are statistically better. It's more robust to noise. It can extract more complicated structures, but it may require higher learning time. It may be slower, so computationally it's worse. But on the other hand, if we are only given a lower budget on computations, then we can use a faster algorithm. We have to use a faster algorithm, but that algorithm may be statistically less powerful. So you see there is this trade-off between statistics and computation. And in this talk, I want to quantify this trade-off for the problem of graph clustering. So what's the graph clustering problem? I give you a graph or a network with n nodes. Think about the friendship network over Facebook, for example. And our goal is to identify groups of nodes such that inside the group there are many edges. They are densely connected, and between the groups there are fewer edges. So we want to find these densely connected subgroups of nodes, which we call clusters or communities. And you can think of the edges as representing the similarity between nodes. So finding the clusters means we are trying to find sets of nodes that are similar to each other. So this is the graph clustering problem. We want to cluster the nodes of a graph. And of course, in practice, there are many different applications of this abstract graph clustering problem. It's used in finding communities in a social network. It's used in finding groups of functional genes or proteins in biology. It's used in identifying groups of similar customers such that you can do personalized recommendation. So this is a problem that is of practical interest, but in this talk I'll focus on the theoretical aspects of this problem to try to understand the statistical and computational issues in graph clustering. And to do that, I need a mathematical model for graph clustering. And one of the most popular models for graph clustering is the so-called stochastic block model, also known as the anti-partition model. So the model is very simple. So suppose that I have n nodes, and there are R clusters of these n nodes that we don't know, and each of them has size s. And what we do observe is a graph that is generated from these n nodes and these underlying clusters. And we generate the graph in a probabilistic way. So this is the adjacency matrix of the graph, and we generate this graph by placing an edge between two nodes with some probability p if these two nodes are in the same cluster. And we place an edge between two nodes in different clusters with a different probability q. And you can think of p being larger than q. So I have more edges inside the clusters. I have fewer edges between the clusters. And the goal is that I give you this adjacency matrix of the graph. You want to find out these underlying clusters that generate this one. And of course, when I give you this adjacency matrix, it's not ordered like this. It will look like a random noisy matrix, but you still want to find out the clusters.
Are you assuming that R times S is equal to N? Does every node belong to only one cluster?
Yeah, so I don't require every node to belong to a cluster. There might be nodes that are not in any clusters. So R times S can be smaller than A.
But you assume all the clusters have the same size S? Is S known?
I'll talk about that in the next slide. Yes?
Are you going to define the cluster? Because I don't know what exactly, like what's the mathematical definition?
So clusters are just a few subsets of nodes that do not overlap with each other. We assume that there are these ground truth subsets of clusters. And our goal is, given this graph that is generated according to these clusters, we want to recover those clusters.
What is a cluster?
A cluster is a subset of nodes that we assume exist, but we don't know.
Does it satisfy like certain properties?
The connection is probability.
So
His question is with probability P what?
That there's an edge between any two nodes within this set.
So I assume that there is already these different subsets of nodes, let's say G1 to Gn, and if for each node, if it is in some Gi, then I'll place an edge between them with some probability P. And otherwise, I'll place an edge between them with probability Q. So I assume there's these ground truth clusters.
Okay. I guess you're thinking of P being typically larger than Q.
Yes. So any other question about the definition of the problem? And for those of you who have worked on, say, the plenty partition problem, or plenty clique problem, or plenty or graph clustering problem, these are all special cases of this model. And this is the question that I want to answer. So I'll consider algorithms with different computational complexity, with different running time. And I want to know for each of these algorithms, for what values of these parameters, the edge probability, the cluster size, the number of clusters, the number of nodes, for what values of these problem parameters, such that that algorithm can recover the underlying clusters given the graph. And I'm also interested in the Convex problem, which is for given values of these model parameters, how much computational resource, how much running time do I need in order to recover the underlying clusters. So I want to understand the statistical performance of algorithms with different computational complexity. And in this talk, just to simplify things, I'll focus on exact recovery of the clusters. So I want to recover the cluster membership of every node. But some of these results can be generalized to approximate recovery. And going back to your question, just for simplicity, we assume that all these parameters are known to the algorithm. And we assume that all the clusters has the same size, all the node pairs between all the node pairs in a cluster has the same edge probability, and these assumptions can be relaxed. I'll talk about this later, but it's not essential. Yes?
Sorry, will you talk about inexact recovery with a loss function or something later as well, or?
Not in this
today?
talk. Yeah, not today.
Just as a quick question then on that, do the sort of results look qualitatively different in an inexact case, or are they somewhat similar?
Similar. For the most part, they're similar. Or, in other words, that there are actually a more general results which cover exact recovery as the special case. But you can just quantify the number of misclassified nodes as a function of these parameters. Yes?
Would you give us a rigorous definition of what exact recovery means? Because I'm assuming that even though a node belongs to a cluster, if we're very unlucky, right, it may not be connected to anything from that cluster, you're not really asking for algorithm to recover membership of that node with probability 1.
We want a high probability result. So of course, if a node has no neighbors, it's not connected, there is no way I can recover its clusters. So we need some of these probabilities to be large enough such that we don't run into that problem.
So the word exact refers to what?
Refers to I recover the cluster membership of every node, not
Probably
just.
are you going to send S to infinity?
No, all these results are actually finite sample results. So by exact recovery, I mean recovering the membership of all the nodes, not just most of the nodes. And so this is the results are non-asymptotic, but you can take n goes to infinity, and we allow the number of clusters to grow with n. So our results apply to the more general case where you can have a growing number of clusters, not just a constant number of clusters. But that is actually not very important for this talk. So let's first look at the statistical aspects of this of this graph clustering problem. So remember that we have 5 parameters: the number of nodes, number of clusters, size of the clusters, edge probability inside the cluster, and edge probability between the clusters. And the problem is harder statistically if the difference between P and Q is smaller. The difference between the in-cluster and cross-cluster edge probability is smaller because the cluster structures is less obvious from the data. And the problem is harder statistically if P minus Q is fixed, but P gets larger because each edge is a validity variables, and when P gets larger, the variance gets larger. So this leads to a harder problem statistically. And also the problem becomes harder if the size of the cluster becomes smaller, because you can have potentially more clusters, and the structures are more complicated, and the signal is smaller. So these are all the parameters that determines the statistical hardness of the graph clustering problem.
What if S is small but R is fixed? Is it still harder?
Still harder.
Just because more nodes do not belong to any cluster? Because R is the number of clusters. Right?
So you can think of a cluster as the signal, and the size of the cluster determines the magnitude of the signal. So if S is smaller, it's harder to identify these clusters from many nodes. And so our questions becomes, for a different algorithm with some computational complexity, how does this ratio P minus Q squared divided by P need to scale with all the other parameters in order for that algorithm to guarantee exact recovery of the clusters? So you can think of this ratio as the signal to noise ratio. P minus Q is the signal in your problem. P measures the variance of the noise. And we want to understand for what SNR we can recover the clusters, the underlying clusters. Now I want to understand the relationship between the SNR and the other parameters of the problem. The number of nodes, the number of clusters, and the number of and the size of clusters. And this is a slide that summarizes all the results in this talk. So just for simplicity, I'll assume that this signal to noise ratio scale with the number of nodes in this way. It equals n to the power of minus alpha, and the size of the cluster scale as n to the power of beta. So as alpha increases, this signal to noise ratio becomes smaller. So you get a harder problem. So when alpha increases from 0 to 1, you get a harder problem, statistical. And if your beta increases from 0 to 1, your clusters becomes larger. So you have bigger clusters here, smaller clusters here. So in this two-dimensional plot, each point represents a graph clustering problem with specific values for P and Q and S and N for all the following parameters. So think about this as the space of all graph clustering problems.
So actually, come back to Alex's question of since you're defining everything as parameterized by n, should we think of probability of correct recovery as being that you recover the graph with probability more than 1 minus 1 over n to the poly, or
Yes.
not
Exactly.
exponentially fast, right? I mean, we could, like, it would change if you do 1 minus exponentially faster.
So we will focus on 1 minus poly n.
1 minus 1.
So for some of the algorithms, we can actually get an exponential probability. But just
This
to make
chart is for 1
this
minus
chart is for poly n. So if we look at this space of all graph clustering problems, it turns out that, so if you go to this direction, you get a problem that's statistically harder because I have smaller SNR and smaller clusters. And it turns out that this space can be partitioned into several regions. In this blue region, the problem is statistically easy. And it is easy enough that we can use a very simple algorithm, actually a linear time algorithm, to recover the clusters if your problem falls into this region. And if you go a little bit right, the problem becomes statistically harder. And in that case, this simple algorithm provably fails. But there's another algorithm, which is a polynomial time algorithm. It takes more than linear time, that works in both this green and blue region. And if we go further down, the problems become statistically even harder. And in this region, we don't know so far a polynomial time algorithm for the problem. But if you analyze a super-polynomial time algorithm, you can show that it actually works in this region. And if we go further right, then the problem becomes statistically so hard that all algorithms, regardless of its computational complexity, will fail to recover the clusters in this gray region. And in fact, we can show that this particular linear time algorithm will fail provably in this red, blue region. This particular polynomial time algorithm will fail in this red region. We conjecture that there is no polynomial time algorithms in this red region, but it's a conjecture, so there is a question mark here. But
The statement about the gray triangle, is it a conjecture or a theorem? No known algorithm succeeds?
Yeah, this is a theorem that you can prove that no algorithm, no matter regardless of polynomial time or super polynomial time algorithm, cannot work here, because here the SNI is so small that there is just not enough information in your data to recover the cluster. So here you'll see there is a trade-off between statistical and computational considerations. If I use a computationally more expensive algorithm, we can recover the clusters for a larger region of the parameter space. And if I use a simpler, faster algorithm, then I can only work with a smaller region of the parameter space. I can only deal with problems that are statistically easy. And in this talk, I will explain each of these regions and what algorithms we use. But if I do there, any question about this plot? And again, I focus on exact recovery. So by succeed, I mean recovering the clusters exactly with high probability. And by fails, I mean it will output the incorrect cluster with high probability. Yes, hiding all the log factors and constant factors. In the theorem, we do have the factors, but in this class, I just hiding off. All right. So let's first look at the simple region where you can use a very simple algorithm to recover the clusters. And this is a somewhat trivial algorithm. So we just look at each pair of nodes, count how many labels that it has, and then we declare these two nodes to be in the same cluster, if and only if they have many neighbors. If the number of neighbors, common neighbors, exceeds some threshold. So for example, here we look at these two green nodes. They have 4 common neighbors, and we compare the number of common neighbors with some threshold. We actually have a correspond expression for that threshold, assuming we know all these parameters. And then we compare with this threshold. If it's large, we declare it to be in the same cluster. Otherwise, we declare that they are not in the same cluster. And the results we get may not be consistent. And if it's not consistent, I just declare failure. And I want to understand when does this simple neighbor counting algorithm recovers the underlying true clusters. And while this algorithm is very simple, it's actually used as a subroutine in many more complicated algorithms. So it's an algorithm of interest. And let's first look at the computational aspect of the problem of this algorithm. You can show that the running time is R times the number of edges in your graph, R being the number of clusters. So this is a linear time algorithm. If your number of clusters is not too large, you can actually improve on the running time if you use better data structure. But all this is a very fast near linear time algorithm. And it's very simple to implement. So computationally, this is a very good algorithm. So how about the statistical performance of this algorithm? When does this algorithm recover the underlying clusters? And this is our theorem. So we can show that this simple neighbor counting algorithm recovers the underlying clusters with high probability if this condition is satisfied. So recall that this left-hand side measures the signal-to-noise ratio in your problem. So as long as the signal-to-noise ratio is larger than square root of n divided by s, then this counting algorithm probably succeeds. And I'm ignoring some constants here. And we can prove that the converse is also true, that if this condition is not satisfied, if the SNR is smaller than this expression, then this algorithm fails with at least a constant probability. So this corresponds to this boundary in dot plot. If you're on this side of that boundary, this condition is satisfied, this simple algorithm works. And if you're on the other side, then this algorithm probably fails. So this characterizes this green simple region of the problem.
Could you say one more word about the computational complexity description of this algorithm? I found it counterintuitive because R makes an appearance. In the way the algorithm is structured, I'm basing everything on the local connectivity I observe rather than the total number of clusters I expect to see. So is this the expected running time somehow?
No, that is an upper bound of the running time. So imagine a very dumb algorithm that I first look at a pair of nodes, look at their common neighbors, and when I look at the common neighbors, I only I can use the sparse representation of the graph. So the complexity would depends on the number of edges in that graph. And I will recover, when I run this algorithm, I will recover the clusters one by one. I'll look at a pair. If I declare it in the same cluster, then I will look at the neighbors of that pair and try to see if they are in the same cluster. So somehow, this is a particular implementation of this algorithm. It takes time that scales with R. But I'm sure that you can use better data structure to improve, to hopefully get rid of this dependence of R.
When you say linear, is linear with n?
With the number of edges. That is the
N squared.
that is roughly Pn squared. And so P can be something like 1/n. So this is the time that you need to read the data. So we don't expect that we can do that.
I have a question about the algorithm.
Mhm.
Like, what if we have 3 nodes? Like,
Mhm.
the first one, the second one have a lot of neighbors,
Mhm.
and the second one and third one have lots of neighbors, but the first one, third one doesn't have any neighbor.
Mhm. So I would declare the first and second node as in the cluster, the second and third as in the same cluster, the one and third as not in the same cluster. The result is not consistent. So my algorithm just outputs failure.
Or fair.
So by succeed, I mean it recovers it's consistent and it equals the underlying cluster exactly. Yes.
So I still don't know what WPAL is.
With probability at least.
Oh, at least. So that's a finite time result. Is there
Yes.
any constant missing there?
Yes, I'm hiding all the constants.
Okay.
But I do
including-
keep the log factors.
Including in the probability statement, the 1 minus 1 over n.
So this is a lower bound of the probability. And that constant here determines the exponent here. I just pick up
I got you.
some constant.
So just to clarify the second part,
Uh-huh.
the probability happens for n sufficiently large, or for all n larger than a certain n. It's probability at least half.
Yeah, and that's the same as putting a large constant there, or a small constant. All right, so this characterizes this green region. And of course, if I'm given more computational resources, more time budget, we ask the question, can we do better in polynomial time? And to get a better polynomial time algorithm that works in both the green and blue region, we will start from looking at the maximum likelihood estimator of this problem. So remember that we use the stochastic plot model to generate a graph given some underlying clusters, so we know the probability of observing that graph given some underlying clusters, and we can just maximize this probability over all possible clustering of n nodes. So this is the maximum likelihood estimator for finding the clusters. And of course, this is a non-convex algorithm because we need to look at all possible clustering of n nodes, and there are exponentially many of them. And we don't know a better way to solve this maximum likelihood estimator than just enumerating all possible clustering. So this is a non-convex algorithm. It requires super-polynomial time. And to get a polynomial time algorithm, our idea is to use convex relaxation to relax this non-convex problem into a convex one. So maximizing the likelihood is the same as maximizing the log likelihood. And just to parameterize this problem, we can represent a clustering, a set of clusters of n nodes using a matrix, n by n, so-called cluster matrix Y. And this matrix is defined as follows. So it's an n by n matrix, and I set Yij equal to 1 if I and Ji are in the same cluster. And otherwise I set it to 0. So cluster matrix will look like this. It's a 0-1 block diagonal matrix. Each block corresponds to one cluster. And I have 1 here because these clusters are in the same, these nodes are in the first cluster, this represents the second cluster, and I have all zeros here. So now, if I use this representation as my variable, I can actually write down the log likelihood in closed form. And I can simplify this a bit. It turns out it is a, so the product becomes the sum if I take it outside the log, and I ignore those terms that does not depend on y, your variable. And then when I simplify it a little bit, it turns out that the objective function becomes a linear function of your variable y being your n by n cluster matrix. So my problem becomes maximizing this linear function subject to the fact that y is a cluster matrix that represents R clusters of size S, which has the form of a block diagonal matrix, a 0-1 block diagonal matrix. So this is a still non-convex problem because of the constraint. The objective is now a linear function of y. But we do know that y satisfies several other properties. We know y is a positive semi-definite matrix because it has this block diagonal structure. We know that each entry of y is 0 and 1, between 0 and 1 by definition. And we also know that the number of ones here equals to R times the size of the cluster square. We assume that we know these parameters. And all these properties, they are convex constraints. So I'll just replace this non-convex constraint with this convex one. So now I need to maximize this linear function subject to several convex constraints. So this is a convex realization of the non-convex maximum likelihood aspect. And it turns out this can be cast as a semi-definite program. It can be solved in polynomial time using interior point methods. And it turns out this is actually SDP with many special structures. In the constraint, we only have a PSD constraint, a linear constraint, and some simple box constraints. So it can be solved by some specialized, faster algorithms like proximal gradient and ADMM. I asked Jim every week that if he has a better algorithm for solving this. So the bottom line is this is a polynomial type algorithm. It's slower than the previous linear time algorithm, but still runs in time polynomial in n. And so computationally, we understand what this algorithm is, and how about the statistical performance of this algorithm. And this is our theorem. So this convex realization of the maximum likelihood estimator recovers the underlying clusters exactly with high probability if this condition is satisfied. So again, we require the signal to noise ratio to be larger than some expression. I'll come back to that expression later. And this is actually a sufficient and necessary condition in the sense that if this condition fails, then this convex realization will not be able to recover the underlying clusters. So again, I'm hiding the constant factors. And if you remember, for the previous simple algorithm, we have the same left-hand side, but on the right-hand side, I have square root of n over s instead of n over s squared. And it's easy to see that this right-hand side is strictly smaller than this one for the previous algorithm. So this convex realization approach works under a less restricted condition. So it works for a larger class of graph clustering problems. And graphically, that condition corresponds to this line here. On this side, that condition is satisfied, the convex realization works. On the other side, it fails provably. So this is an algorithm that is slower, but works for a larger class of problems. And I don't have time to go over the proof. Actually, there is a 2-page proof of this theorem. But if you look at that, so this is just the same condition, the square root of the previous condition. So what's interesting in this condition for the convex relaxation is that there is 2 parts on the right-hand side, and we need the left-hand side to be the first part, and this is a condition that is necessary even if I tell you the cluster members of all of the 1 nodes, but ask you just to recover the remaining 1 node. So we need this condition, the first part, even we know the cluster memberships of n-1 nodes. And the second part corresponding to the price you pay by taking the convex relaxation of MLE. So in practice, we don't know the cluster memberships of all the other n/1 nodes. We need to find their memberships by looking at the global structure of the graph, and we do that by looking at the STT. What the STT basically doing is to look at the spectrum of the graph, and by doing that, we pay a price of this. So this condition has this natural interpretation. Many extensions, so that algorithm is actually a practical algorithm that you can use. It can extend to the case where your cluster size is not equal, extends to the case where you don't know the parameters, extends to the case where the degrees of the expected degrees of the nodes is not equal, and some other settings. So, and we actually apply this algorithm to some real data sets that where it works better than some other existing algorithms. So the point is that although this is a theoretical talk, the algorithms that we mentioned are actually practical algorithms that you can use. And some of you may know the algorithm, the spectral clustering algorithm, where you just take the adjacency matrix, compute its SVD, run a k-means over the top singular vectors of that adjacency matrix, or the Laplacian of the adjacency matrix. So how does spectral clustering fit in this graph? And so it turns out the best theoretical guarantees for spectral clustering looks like this. So if you compare this guarantee with our guarantee for the convex relaxation, it has this extra R factor, the number of clusters on the right-hand side. And this corresponds to this line. So as far as we know, the spectral algorithms is statistically a bit worse than the convex relaxation algorithm. It works for a smaller region of the problem, but the spectral algorithms is faster than solving an STT. So you can see there's another level of computational and statistical trade-off within the class of polynomial time algorithms. And of course, you may wonder, is there other polynomial time algorithms that are better statistically? And our conjecture is that the answer is no. Our conjecture is that there is no polynomial time algorithms that finds the underlying clusters if this condition is not satisfied. So this is the same condition for the success and failure of the convex relaxation algorithm. And if this condition is true, then it means that the convex relaxation algorithm is the statistically optimal algorithms among all polynomial time algorithms. Of course, we haven't been able to prove this conjecture. are many evidence that supports this conjecture. And also note that this is an average case harness conjecture. It's not the P versus NP type of worst case complexity. Because we are looking at a problem that is generated randomly, we are interested with high probability results, not worst case results.
One question.
Yes.
So for the green region, where you say linear time algorithms is enough, so is that one do you need some conjecture as well, or this is actually the exact region, or this is just inner bound, because this only, it seems to be shown based on a specific linear time algorithm. Is there,
Yes. And
does there exist another linear time algorithm that actually can give you a larger region? Or?
We don't know. And we don't even want to make a conjecture there because it seems even harder to classify, to characterize the class of linear algorithm than the class of polynomial time. And again, this is a conjecture with many evidence. So a special case of this conjecture is the point-and-click problem, where P equal to 1, Q equal to, so P and Q are constants. So the point-and-click conjecture is a special case of this general problem. It's a special case that lies on this axis. And the point-and-click problem has been studied by many people. We don't know a polynomial time algorithm when you are under this point. So this is a problem that people widely believe to be computationally hard, and it's a special case of our conjecture. And if you assume that the point-and-click problem is hard, we can actually prove some conditional hardness results. It's easy to see that because on this line, under the 1/2 point, the problem is hard, then all problems below this red line is hard. It's as hard as the point-and-click problem. And people have been, so this is still different from our conjecture, and people have been working on closing this gap. So this is the best results we have so far. But this is another evidence that supports this conjecture. And we have some other ones that I'll just skip here. So the conjecture that is that there is no polynomial time algorithm when you are below this line. But if you don't care about being polynomial time, then there actually exists a super-polynomial time algorithm that works in this red region. And that algorithm is just the original maximum likelihood estimator without the convex relaxation. It's of course computationally expensive to use, but statistically it's a better algorithm. It recovers the clusters when the signal to noise ratio is larger than this expression, and this expression, if you compare with the right-hand side of the condition for the convex relaxation, it only has the first part of that previous right-hand side. So again, this is a less restricted condition than the one for the convex relaxation of the ML. And that this condition corresponds to this line. So we know that if we are on this side of the line, the convex relaxation, the maximum likelihood algorithm recovers the underlying clusters. So this is a computationally expensive algorithm that is statistically better than all known polynomial time algorithm. And now, if we go to this gray region, then we can actually prove that no algorithm will work. And this is our theorem. It says that all algorithm will fail with constant probability if that previous condition is not satisfied, if you are on the other side of that line. And this is true regardless of the computational complexity of the algorithms. And this means that the mathematical estimator is a statistically optimal algorithm because it achieves this limit. So the way to prove that theorem is to use information theory. We can cast our clustering problem as a channel estimation problem in communication. So we have some unknown clustering Y. We observe a graph that is generated from some probabilistic model, and we can look at this model as a noisy channel. So our goal is to, given the output of this channel, we want to recover the input of that channel. And this is a problem that has been studied in information theory. So graph clustering is just decoding the message from an observation of a noisy channel. And from information theory, we know that decoding is impossible regardless of what algorithm you use. If the capacity of this channel is smaller than the entropy, the amount of information that is contained in your source message. And we know the channel exactly, we know this distribution, so we can compute the channel capacity and the source entropy in closed form. And if we simplify this expression, we get that condition exactly. So this is the condition that no algorithm will work, and it's proved using ideas from information theory. So the K should be S here, which is the size of the cluster. And another way to look at this condition is that this is the condition that is required even if I tell you the cluster members of all but one nodes and ask you to recover the remaining cluster, So this is a necessary condition for any algorithm. And as Shane mentioned, so all these results can be generalized to the approximate recovery setting. We can characterize the condition, the sufficient and necessary condition for recurring a given fraction of the nodes. And we use some other tools from information theory. Yes?
If you were to modify your criterion for recovery, right, model probability of 1 minus 1 over n, what would some lower probability? The version of this theorem still exists for the gray region.
So this is one possible extension of this theorem. So if I ask not to recover all the nodes, but recover more than 50% of the nodes, then this condition becomes the same thing less than 1 over s without the log n factor. So if my criteria for recovery, we will less our criteria for recovery from exact recovery to better than a random guess, then the theorem still holds, but the condition will have the same condition without the log factors.
I guess I'm confused about something very simple. Maybe I'm wrong. So when you're talking about exact recovery, you're talking about recovery for all of the nodes in the graph versus a subset.
Yes.
And I was asking about the definition of the recovery, right? You were saying that exact recovery, all of those, but with the probability exceeding 1 minus 1 over n. What if I wanted to recover all of them, but with probability of 1 minus 1 divided by square root of n?
Then you get a different constant here. If you just the same theorem holds. If you just change the exponent of that polynomial, you just change the constant here. And if you change the polynomial to an exponential function in n, then we will have a different condition, and that condition is probably not tight. We're still working on it. So we have a tight condition when we are interested in a polynomial probability. And the exponents of that polynomial only affects the constants, the pre-constants. Yes?
Is the theorem of information theory only asymptotic or
So here we use the Fano's inequality, which works for any n. But so there are some work which tries to characterize the exact constant here. And for those kinds of problems, it's much easier to work with the asymptotic regime than the finite sample regime. So actually, in the asymptotic regime, we know exactly what this constant is. It's something like, I believe, 2. All right, so that's all I want to talk about. That this problem exhibit this trade-off between computation and statistics, in the sense that the space of the problem can be partitioned into these 3 different regions, and the bottom line is that for noisier data, we need a statistically stronger algorithm, which for this problem requires more computational resources. So I'll stop here and I can take some questions.
So you have the parameters P and Q, right?
Yes.
So like specifically like when you were looking at that Facebook graph, right?
Mm-hmm.
How were you computing P and Q? Were you like looking at the actual clusters beforehand and then using that information to compute P and compute Q to feed into your model?
You mean when you use the algorithm or when you try to prove the theorem?
No, when you you got you actually use the algorithm on the Facebook data set, right?
Okay. Yes.
So
okay.
when you did that,
Mm-hmm.
how did you select P and Q? You put some value of P in and some value of Q into your algorithm.
So there is a version of the algorithm which does not require the value of P and Q.
Okay,
It only
now-
requires the number of clusters.
Yeah.
And you can specify the number of clusters. You can guess the number of clusters by, for example, looking at the spectrum of the graph.
Okay. And so like for those results, you were using the algorithm that does not require as input P or Q.
Yes. So there are, as I mentioned, there are many extensions.
The extension.
Yeah.
Where is P and Q in your convex relaxation? I think even the one you had just had R is.
Oh yeah. So the one I present here actually requires knowing the size and number of clusters.
Okay. So
And
we
we-
need just R and S.
Yes, and it requires that the clusters has exactly the same size, but there are more general, more robust version of the algorithms that you only requires knowing the number of clusters or knowing some number between P and Q. Yes?
Could you maybe say a few sentences about how the computational hardness conjecture implemented P, like the relationship between the two? So you had the, yeah,
So the point-and-click conjecture basically says that the problem is hard when you are on this line and you are below 1/2.
Okay.
And the conditional hardness result we have is that it's very simple to say that prove that because you move to the right of this plot, the problem becomes even harder than point-and-click. So we know that anything below this line is as hard as point-and-click. And we can actually do better than that. We can prove that anything below this line is as hard as point-and-click. And the ultimate goal is to prove that anything below this line is hard. Yes.
Implicit, it seems like P is very small, right? In your formulation.
No, it does not require anything about P. So these are finite sample results that holds for.
Like at least is less than half.
What's that?
At least is less than half. Because, for example, you said like when you
I see.
track.
Yeah, so a more general version of this theorem, I have P times 1 minus P. In the denominator, I have P times 1 minus P times N here. So that actually works for both P larger than 1/2 or less than 1/2.
We'll take other questions offline. Let's thank you.